Hi everyone, in this video we will learn about line integrals which are taken not with respect to the curve itself but with respect to x or y. The line integral taken with respect to x becomes a to b. We still parameterize it with the x and y, but now instead of all the square root, so you can think of this to be 0. In the original equation, that's what we had. So if you set this to be 0, you're only left with x prime. And the same thing here, if you set x prime to be 0, then you're left with y prime dt. And that would be the line integral. The next thing that is useful to remember is how to find the equation of a line segment between 2 points r0 and r1. Right? So suppose this is a line. A line is just goes on forever, but a line segment is a part of a line. So suppose this is the position vector r1, and this has a position vector just to r0 and r1. That's the position vector of these. How do I to find the equation of the line segment from r0 to r1? I will use a parameter rt, 1 minus t r0 plus t times r1. T goes from 0 to 1. So what's happening at t equals 0, you are at r0. At t equals 1, if you plug in 1, this disappears, you are here. And between 0 and 1, like 0.5, you will always be on this path. It will be a fraction of r0 added to some other fraction of r1, but you will always move along this line segment. So that's how you would parameterize a line segment, which is useful for the next problem that we're going to solve. So evaluate the line integral of y squared dx plus x dy for two different paths. So now the first path is a line segment from negative 5, 3 to 0, 2. And the second path is the arc of parabola x equals 4 minus y squared from the same 2 points. So let's look at what's going on here. I have a point negative 5, 3, negative 5, negative 3, and I have 0, 2. So suppose I code this with blue, then this is the first path I'm taking. It's just a line segment. First, we got to find the parametric equation of this line segment. So what we have, r0 is a vector negative 5, negative 3. r1 is 0, 2. So rt is going to be 1 minus t r0 plus t r1. What is that? That's 1 minus t negative 5, negative 3 plus t 0, 2, which becomes negative 5, 1 minus t plus t times 0, comma, negative 3, 1 minus t plus 2 times t. So that's negative 5 plus 5t and negative 3 plus 3t plus 2t. So I have 5t minus 5 and 5t minus 3. So my parameterization, the x coordinate is 5t minus t and the y coordinate is 5t minus 3, which means my x prime t is 5 and my y prime t is also 5. So what does my y squared dx plus x dy line integral become? Well, the first part is with respect to x. Parameter t goes from 0 to 1. What is y squared? Y squared is 5t minus 3 squared. And the dx becomes x prime, so we have 5 dt. Plus x dy, which is 5t minus 5. And dy, or y prime, is also 5. So we have 5 dt. Okay, so this one, I'm going to let you complete this. And it should come out to -5/6. So this is a extra credit / video verification. Oh, it's not enough space here. Now the second part, which is an arc of a parabola x equals 4 minus y squared, takes a different route. And basically the question is, will the answer differ or not? Now in the red case, the parameterization is x equals 4 minus y squared and y equals y, so that the line integral y dx plus x dy now becomes -3 to 2. That's because of you're parameterizing using y here. And we have y squared 2y dy, because x prime y is -2y and y prime y is 1, plus 4 minus y squared dy, which becomes -3 to 2, -2y cubed minus y squared plus 4 dy. And this, again, you can evaluate, and the question is it same as above? And if you do this correctly, it should come out to be a different value, which tells us that evaluating the line integral depends on the path that you take, which makes sense because a part of the integral takes into account the arc length. And so if you have a different arc length, you expect the line integral to be different. We can extend this idea of line integral to space. And when we say space, we mean 3 dimension, where you have a curve that is parameterized by x t, y t, z t. Then the line integral becomes pretty analogous to the second to 2 dimension f of x t, y t, z t, and you have this arc length factor, which is the square root of dx over dt squared plus dy over dt squared and dz over dt squared. Now we can have a concise notation here, f of rt, because this is the position vector and this is the magnitude of the position vector. And in special case, if your function is just constant, then this gives the length of the curve. The equivalent of this is in case of surface area, when you take the distribution, density distribution as 1, you get the area. And in triple integrals, if you take the density distribution as 1, you get the volume. So here, in special case, if f of the position vector is 1, then you just end up with the arc length. So how we do that is we evaluate each of these expressions in terms of t. So for example, evaluate the line integral y sine z ds, where c is the circular helix given by equation cosine t sine t t. Now this is something you have seen in previous class again, where the shape of this curve, because of cosine and sine on the x-axis, is circular, but because with time it also rises up, it becomes a helix. So the parameter in this case is given to us, and all we have to do is plug in the values. So y sine z ds over c becomes 1 full circle, or 0 to 2 pi, 1 full turn of the helix. Y is sine t, and you have sine z, which is also sine t, and then you have the square root. The derivative of x prime is negative sine t squared. Derivative of y is cosine t squared. Derivative of t is 1. So you have 0 to 2 pi sine squared this becomes 1. So the whole thing is just root 2 dt, and this is root 2 pi, because we know from a lot of our previous integrals that integral 0 to 2 pi sine squared 2 dt gives us pi, after using the half angle double angle formula, converting it in terms of cosine 2t. Let's look at another example where we don't have a one piece path but a multiple path scenario. So in this case, evaluate a line integral given by y dx plus z dy plus x dz, where c is a line segment from 200 to 345. So we have y, x, c. We're going from 200 to some 345, and then from 345 we're moving down to its projection on the xy plane 340, which means we have to use the line segment formula. It's going to be 1 minus t times 200 plus t times 345. Let me color code it so that this is for this particular line. So that's going to be 2 minus 2t plus 3t, or 2 plus t, then a 0 plus 4t, and a 0 plus 5t. So that's my x, that's my y, or xt, yt, ct. So my line integral now is y dx, so y is 4t, and this also means x prime t is 1, y prime t is 4, z prime t is 5. So y dx is just 1, so this is 4t dt. Z is 5t, and its dy, where dy is 4, so 4 dt plus x, which is 2 plus t, but dz, which is 5, so 5 dt. So if we add this all up, you get a 20t, 24t, and a 5t, so 29t plus a 10 dt, going from 0 to 1, that's 29 over 2 plus 20, plus 10, sorry. 49 over 2 is 24.5. And then you work with the second one. So now our t is 1 minus t, going from 345 to 340, which becomes 3 minus 3t plus 3t is 3. Then you have 4 minus 4t plus 4t is 4. And 5 minus 5t plus 0 is 5 minus 5t. So that's your xt, that's your new yt, that's your zt. X prime is 0, y prime is 0, and z prime is negative 5. So what does the integral now become? Most of it becomes 0 because x prime and y prime are 0. So these two become 0, and we are only left with x dz. So x is 3, dz is negative 5 dt, 0 to 1 gives negative 15. So adding, we get the net to be 24.5 minus 15, which is 9.5. Now for an application of this is work done. In physics, you learned that the work done, W, by a force F in moving an object along C is basically the force multiplied by the displacement. Right? So in this case, that would be the force vector dot product with the tangent vector, which is F dot T ds, where T is a unit tangent vector. Okay, so from there we get this definition that if f is a continuous vector field on a smooth curve C given by a vector function RT, then the line integral of f along C, f dot dr, is this, which we saw, magnitude, sorry, is the same as f dot t ds. For example, find the work done by the force field x squared I cap minus xy j cap in moving a particle along the quarter circle given by cosine t I cap plus sine t j cap for t between 0 and pi over 2. So this is just another way of giving you the curve. The fact that it's cosine t I cap plus sine t j cap means that it's a circle. The fact that it's between 0 and pi over 2 means that it's only a quarter circle. And then you have some of this force field, right? So if you look at this force field, for different values, whenever x is 0, there is nothing. So there's nothing on the x-axis. When x is really small, it is kind of small. So, and as x increases, it increases in size, magnitude, sorry. And we are trying to find the work done in moving some object along this circle against this force. Right, so we have f of RT is going to be cosine squared t and negative cosine t sine t. And r prime t is negative sine t cosine t. So the work done is going to be the line integral of f dot dr. So it's 0 to pi over 2, dot product of these two vectors is going to be negative cosine squared t sine t minus cosine squared t sine t dt. So that's just negative 2 cosine squared t sine t dt. Now from a previous discussion, you know what to do when you have cosine raised to m and sine raised to n, which is you will use a substitution. So if you use u equals cosine t, this is going to work out to be negative cosine t cubed t over 3 from 0 to pi over 2, where pi over 2 cosine is 0, but at 0 it's 1, and the two negatives become a positive to give you a 2/3. Oh, actually, wait. This is going to be positive. The 0 minus, there will be another negative, so this will come out to be negative 2/3. Okay, so that's it for this video and the idea of line integrals, although we will be doing in the following section the fundamental theorem of line integrals and also learning about conservative forces, etc. Alright, that's it for this video. Thanks everyone.